So, welcome everyone. Today I'm going to talk about the third lesson, which is the multiplication rule and permutation. So, in case that your basics is you feel like basics is not strong enough or you are not confident enough, these videos, which is the introduction to the probability, will help you solidify that stuff. Okay? Because we will need this a lot more. So, consider an experiment with two following characteristics. First, this experiment is performed in two parts. Second, the first part has m possible outcomes, namely x1 to xm, and regardless of which one of these outcomes occurs, the second part of the experiment has n possible outcomes, y1 to yn. So, if we use the concept of the simple sample space that we have for last time, assuming that the probability of each combination that occurs is equally likely. So, we can list the outcome as this x1 y1 up to x1 yn and until xm y1 up to xm yn. And we can see that there are m rows and n columns. So, the sample space S contains m times n column and m times n outcomes. So, this basic stuff is called the multiplication rule. Let's formalize this. Suppose that an experiment has k parts, where k is greater than or equal to 2, and I part of the experiment can have ni possible outcomes, where I is equal to 1 up until k. Also, all of the outcomes in each part can occur regardless of which specific outcomes have occurred in the other parts. Then, sample space S will contain all vectors u1 to uk, where ui is one of ni possible outcome of I part. Hence, the total number of these vectors in S is equal to n1, n2 times up to nk. So, this formula seems simple. You just multiply all the terms. But, you must make sure that this condition is satisfied. Namely that the outcome in each part can occur regardless of which specific outcomes have occurred. But sometimes, this condition doesn't hold true, but the formula still holds true. But we should be a little bit careful in applying this formula. Okay? So let's look at the first example. Consider an experiment where a card is selected and removed from the deck of n different cards. A second card is then selected and removed from the remaining n-1 cards. And finally, a third card is selected from the remaining n-2 cards. So, technically, it is called sampling without replacement. Because once we sample one card out of n card, we remove them. We did not put it back. Okay? So, what can we say about it? First, any one of the n cards should be selected. N outcomes, surely. Then, once this card is removed, any one of n-1 cards could be selected. Okay? And similarly, finally, once the second card is removed, any one of n-2 cards could be selected. That means, so if you look at it carefully, the condition of the multiplication rule doesn't hold, right? Because different cards being selected leads to different outcomes. However, the number of outcomes is still the same. So, as I have said before, even though the condition doesn't hold true, but if let's say the number of outcomes is still the same, we could still apply the multiplication rule. Okay? So the number of total possible outcomes is n times n-1 times n-2. And as I've said before, right, this just repeat what I said, is that the generalized version of multiplication rule doesn't require that the condition, whatever happens in the previous one, the outcome is still the same. But just that the number of outcomes is still the same. We can apply this version also. And next concept that we're going to talk about is the permutation. Permutation, the number of distinct orderings of k items selected without replacement from a collection of n different items is we denote it as p of nk, which is n factorial over n minus k factorial. So, in the last example, we could apply this also, right? Because in the last example, we have n as the number of cars, and k is equal to 3, right? And we could make sure that the formula still hold true because n factorial over n minus 3 factorial. This is the same answer as n times n minus 1 times n minus 2, right? Okay, let's look at the second problem, the birthday problem. So, the problem is simple enough. We would like to find the probability that at least 2 people in a group of k people will have the same birthday. So, how do you find it? First, we must assume that the birthday of k people are unrelated, and each of 365 days of the year is equally likely to be a person's birthday. This isn't true in reality, okay? But we assume this for simplicity because we want to find the simplified version so that we can get some insight about it. So, the trivial case is that if k is greater than 365, surely the probability is equal to 1, okay? Because the number of people is greater than the number of the birthday. But if k is less than or equal to 365, we can talk about the probability now, okay? The probability that all k birthday will be different is permutation of 365 selected k over 365 over k. Because 365 over k in the denominator is the choice that could be chosen by each person because they are unrelated. We could use the multiplication rule in this case. And the above one we apply the last formula about the permutation. Okay? So, that is all k birthday will be different, but we are not interested in that. We are interested in at least 2 people will have the same birthday. We could have 1 minus this one. So, this formula seems simple enough because we could apply just the simple concept of the permutation and the simple concept of the multiplication rule. But let's just guess. Let's say in order to obtain the p value of p, that is the probability that at least 2 people will have the same birthday greater than 1/2, how many people are needed? Surely it must be less than or equal to 365, but how much? How many? You may guess, let's say 100, or let's say 150, and that's kind of, let's say they seems like a very small chance, right? But if you plug in this number, we plug in this